22 billion kilometers from where you are sitting right now, a machine built in the 1970s, using less computing power than the key fob for a modern car, is sailing through a region of space that has no sunlight, no warmth, and, according to almost every model scientists had built before it got there, should have almost nothing in it at all. That machine is Voyager 1, and for more than a decade now, it has been quietly sending back a signal that genuinely confused the very people who built it. Out in that supposed emptiness, in a place so far from any star that the sun is just another point of light in the sky, Voyager 1 detected something it was never designed to find. A persistent, measurable pressure pushing against it, coming from matter that, according to the maps humanity had drawn of interstellar space, simply should not have been dense enough to produce that kind of push at all. This is not a conspiracy theory, and it is not exaggerated internet clickbait dressed up as science. It is a real finding, confirmed by NASA's own Jet Propulsion Laboratory, published in peer-reviewed journals including Nature, Astronomy, and Science, and it forced physicists to rethink some of their basic assumptions about what the space between the stars actually looks like. The story of how a 45-year-old spacecraft, running on decaying plutonium and 1970s-era electronics, stumbled into one of the strangest environmental puzzles in modern astrophysics, is genuinely one of the most quietly astonishing tales in the entire history of space exploration. To understand why this discovery mattered so much, you first have to understand exactly what Voyager 1 was built to do, and how spectacularly it exceeded even its own most optimistic original mission plan. Voyager 1 launched from Cape Canaveral on September 5, 1977, riding a Titan IIIe rocket into the sky roughly 2 weeks after its twin, Voyager 2, had already lifted off on a slightly different trajectory. Despite launching second, Voyager 1 was placed on a faster path through the solar system, and actually overtook its sibling in December of that same year. Both spacecraft were part of what engineers originally called the Mariner Jupiter-Saturn mission, a name so unglamorous that NASA eventually held a public competition to rename the project, settling on the far more evocative title Voyager. The core engineering mission was audacious for its era. Take advantage of a rare planetary alignment that occurs only once every 176 years, one that would let a spacecraft use the gravitational pull of Jupiter to slingshot itself towards Saturn, gaining speed and changing direction almost for free, using only a fraction of the fuel a more conventional flight path would have required. Voyager 1 swung past Jupiter on March 5, 1979, discovering a faint ring system around the planet and identifying two entirely new moons, Thebe and Metis, along the way. It then continued on to Saturn, making its closest approach on November 12, 1980, where it found 5 new moons and an entirely new ring, and where it also completed a close flyby of Saturn's massive moon Titan, specifically to study its thick, hazy atmosphere. That flyby of Titan came at a real cost because the trajectory needed to study Titan closely bent Voyager 1's path sharply upward, out of the plane in which all the planets orbit the Sun, permanently ending any possibility of the spacecraft visiting Uranus or Neptune the way its twin eventually would. From that point forward, Voyager 1's entire remaining mission became something nobody had originally planned for in detail, an open-ended journey outward, forever, into the unknown darkness beyond the last planet. Voyager 1 is an astonishingly small and fragile-looking thing to have accomplished what it has. At launch, it weighed just 815 kilograms, roughly the weight of a small car, and it carries 11 scientific instruments designed to study everything from magnetic fields to cosmic ray particles to plasma waves. It has no batteries in the conventional sense and could never survive on solar panels this far from the Sun. Instead, it draws its electricity from 3 radioisotope thermoelectric generators, compact devices that convert the heat given off by the natural radioactive decay of plutonium-238 into usable electrical power. At launch, those generators produced approximately 470 watts total, roughly enough to power a couple of hairdryers, and that number has been steadily declining ever since, losing a small amount of power every single year as the plutonium fuel slowly decays and the machinery generating electricity from that heat gradually degrades. Engineers have had to systematically and permanently shut down one instrument after another over the decades, specifically to conserve enough power to keep the spacecraft's remaining instruments and its transmitter alive, a slow, deliberate process that NASA engineers themselves have described in strikingly blunt terms as something closer to palliative care for a dying but still remarkably lucid patient. And yet, despite running on hardware that predates the personal computer, communicating with Earth through a single dish antenna out in the Australian outback, and operating at a distance where a single radio signal now takes more than 20 hours to travel one way at the speed of light, Voyager 1 is still talking. It remains, to this day, the single most distant human-made object in existence, a title it has held since it overtook the more slowly moving Pioneer 10 probe back in 1998. And unless something faster is launched in the meantime, Voyager 1 is expected to hold that distinction until at least the year 2070. For decades, Voyager 1's entire scientific identity was built around the planets, Jupiter's swirling storms, Saturn's intricate rings, the strange hazy orange atmosphere of Titan. But the truly historic and genuinely unprecedented phase of its mission didn't actually begin until August 25th, 2012, when Voyager 1 became the very first human-made object in history to cross what scientists call the heliopause, the outer boundary of an enormous invisible bubble called the heliosphere. That heliosphere is essentially the sun's zone of influence, a vast region inflated by the constant outward rush of charged particles known as the solar wind, streaming outward from the sun in every direction and creating a kind of protective cocoon around the entire solar system, planets and all. Far beyond the orbit of Pluto, at distances measured in the tens of billions of kilometers, the pressure of that outward flowing solar wind finally weakens enough that it can no longer push back against the material drifting through the wider galaxy. And at that specific boundary line, the heliopause, our sun's bubble, effectively ends, and true interstellar space, the space between the stars themselves, genuinely begins. Crossing that boundary made Voyager 1. We were one of the first spacecraft in history to actually leave the neighborhood of our own star and begin directly sampling the material that fills the vast ocean of space between solar systems, something no human instrument ever in the entire history of scientific instrumentation had done before. Before Voyager 1 actually crossed that boundary, scientists had built reasonably detailed theoretical models predicting exactly what interstellar space should look like once a spacecraft finally got out there to sample it directly. And one of the clearest predictions concerned plasma density. Inside the heliosphere, out near the very edge of the solar wind's influence, the density of charged particles was expected to be extremely low, something in the neighborhood of roughly 0.002 particles per cubic centimeter. Once a spacecraft crossed into true interstellar space, models predicted plasma density should jump dramatically, up to somewhere around 0.1 particles per cubic centimeter, a sudden and dramatic increase that would itself serve as one of the clearest possible signatures, confirming that a spacecraft had genuinely left the sun's bubble behind. In April of 2013, Voyager 1's plasma wave instrument detected exactly that kind of jump, picking up locally generated electron oscillations, vibrating at a frequency corresponding to an electron density of approximately 0.08 particles per cubic centimeter, remarkably close to the theoretical prediction, and providing NASA scientists with the crucial confirming evidence they needed to formally declare that Voyager 1 had indeed crossed into interstellar space. It was, in that specific narrow sense, exactly what everyone expected to find. The real surprises were still waiting. The plasma density readings didn't simply jump once and then settle down at the predicted baseline level the way the original model suggested they should. Instead, as Voyager 1 continued its outward crawl through the years that followed, researchers monitoring its data noticed something the theoretical models had never actually predicted. Plasma density kept rising. According to detailed analysis published by NASA's Jet Propulsion Laboratory, electron density around Voyager 1 began climbing in 2013 and kept climbing steadily until it reached its highest measured levels by around mid-2015, representing an increase of roughly 40 times the density that had first been detected. At the moment the spacecraft initially crossed the heliopause boundary, this wasn't a brief spike or a temporary anomaly caused by some passing disturbance. The elevated density persisted, holding at that dramatically higher level with some fluctuation. Across the entire multi-year dataset, scientists analyzed running from that initial crossing all the way through early 2020. A 2019 analysis drawing on Voyager data specifically examined the pressure balance occurring right at the boundary zone, where the outward push of the sun's solar wind, moving through a region called the heliosheath, meets the inward push of the surrounding interstellar medium, the very local mixture of gas, dust, and charged particles that fills the space between star systems in our particular corner of the galaxy. In theory, at the exact heliopause boundary itself, these two competing pressures, the sun's bubble pushing outward and the wider galaxy pushing inward, should balance out reasonably close to what existing models predicted. Instead, NASA astronomers analyzing this pressure balance using real Voyager measurements found that the actual pressure detected in that distant borderland zone was measurably higher than what models had anticipated it should be, describing the finding, in refreshingly plain language for a scientific announcement, as simply not what they had anticipated finding out there at all. The universe, it turned out, was pushing back against our sun's protective bubble noticeably harder than physicists had calculated it should. Then, in 2021, the story took its strangest and most genuinely unsettling turn yet, when a research team led by Cornell University astronomer Stella Koch-Ocker, working alongside longtime Voyager scientist James Cordes, published findings in the journal Nature Astronomy describing something entirely new buried inside years of previously unexamined Voyager 1 data. Historically, Researchers had only been able to measure interstellar plasma density during rare, dramatic events, specifically powerful shock waves, triggered whenever the sun experienced a major solar outburst, sent a burst of charged particles rippling outward through the solar system. And that shock wave eventually reached Voyager 1's location out in interstellar space, causing the surrounding plasma to noticeably vibrate, almost like plucking a guitar string, in a way the spacecraft's instruments could detect and measure. James Cordes described these dramatic shockwave events using a memorable weather metaphor, comparing them to detecting the sudden crack of a lightning strike during a passing thunderstorm, sharp, obvious, and impossible to miss, but also relatively rare and separated by long stretches where scientists genuinely had no way to measure the surrounding plasma at all. But while painstakingly combing back through Voyager 1's electric field data collected between 2017 and 2020, the research team discovered something nobody had specifically been looking for: a persistent, faint, and remarkably steady signal hiding quietly in the background of the data the entire time, a signal researchers eventually began describing, almost poetically, as the faint, persistent hum of interstellar gas itself. If the dramatic shockwave events were like isolated claps of thunder, this newly discovered signal was more like a continuous, gentle rain, always present, always measurable, running quietly underneath everything else in the data the entire time, essentially unnoticed for years, simply because nobody had thought to look for something that subtle and that persistent. The genuine scientific significance of discovering this steady background hum went well beyond simply finding a curious new sound in the data. Because this newly identified signal was continuous rather than sporadic, it meant that for the very first time, researchers could measure interstellar plasma density constantly and consistently along Voyager 1's entire ongoing trajectory, rather than only during the rare, isolated moments when a solar shockwave happened to sweep past and trigger a detectable vibration. That shift from occasional isolated snapshots to a continuous stream of measurements allowed scientists to construct what researchers themselves described as the most complete map yet assembled of plasma density in the interstellar medium immediately surrounding Voyager 1's path. And what that continuous new stream of data revealed was genuinely unexpected on its own terms: small-scale density fluctuations occurring across distances of roughly 1 astronomical unit, the same distance separating the Earth from the Sun, fluctuations that researchers now believe are direct evidence of ongoing turbulence rippling through the interstellar medium itself, subtle waves and eddies moving through the sparse material that fills the space between the stars, constantly stirring and reshaping the very environment Voyager 1 continues to fly through today, more than a decade after first crossing into that vast and evidently far busier than expected region of space. It's worth pausing here to genuinely sit with just how strange and counterintuitive all of this actually is, because most people, quite reasonably, picture interstellar space as close to perfect, total emptiness, an absolute vacuum with essentially nothing in it at all. And in the most literal sense, compared to almost any environment on Earth, that intuition is basically correct. The density Voyager 1 is detecting out there, even at its unexpectedly elevated levels, still amounts to something on the order of a tenth of a single particle crammed into an entire cubic centimeter of space, a level of near total emptiness that no laboratory vacuum chamber built by humans on Earth could ever practically replicate or come remotely close to matching. But near total emptiness and mathematically perfect, unchanging, predictable emptiness turn out to be two genuinely different things. And it's specifically that second assumption, the idea that interstellar space should be smooth, largely uniform, and closely predictable using existing models, that Voyager 1's actual measurements have been steadily and repeatedly complicating year after year. The pressure pushing back against our solar system's protective bubble is measurably higher than models predicted it should be. The density of the material out there isn't simply a flat, boring baseline number the way early theoretical models suggested. It fluctuates, it ripples. It shows genuine and measurable evidence of turbulence, actual physical movement and structure occurring within a region of space that most people, quite reasonably, assumed should be almost entirely static and empty. What actually explains this unexpected extra pressure and elevated density remains, even now, a genuinely open and actively studied scientific question. And it's worth being honest and specific about that, rather than manufacturing a tidier answer than the evidence currently supports. Some of the leading working explanations scientists have proposed center on the idea that our solar system doesn't simply drift through a uniform, evenly distributed sea of interstellar gas. Instead, it's currently passing through a specific, unusually structured region of the interstellar medium, sometimes referred to as the local interstellar cloud, an area whose exact density, temperature, and physical structure was never precisely known ahead of time because, quite simply, no human instrument had ever actually been inside it to measure it directly before Voyager 1 got there. Other researchers point to specific solar activity itself as a contributing factor, since powerful solar outbursts sweeping outward from the sun appear capable of physically compressing and disturbing the surrounding interstellar material, even after those outbursts have crossed the heliopause boundary and technically left the sun's direct zone of magnetic influence behind, effectively rippling outward and stirring up the very interstellar material that Voyager 1 is simultaneously trying to measure in what researchers had originally hoped would be its undisturbed natural state. Researchers working directly with the Voyager data, including scientists at NASA's Jet Propulsion Laboratory, have been refreshingly candid that they are still actively working to build physical models capable of properly explaining exactly how and why this persistent background hum of plasma noise is actually being generated in the first place, treating it as a genuinely open frontier of ongoing research rather than a fully solved mystery with all the answers already neatly filed away. There is something quietly remarkable, almost poignant, about the specific way humanity ended up making this particular discovery, and it's worth sitting with for a moment before moving on. Voyager 1 was never built or launched with the goal of measuring interstellar plasma turbulence. Its original 4-year mission, back in 1977, was designed to study Jupiter and Saturn and then, mission accomplished, quietly fade into obsolescence somewhere out past Saturn's orbit. Nobody on the original engineering and science teams that built Voyager 1 in the early 1970s could have reasonably planned for or specifically anticipated a scenario in which their spacecraft would still be functioning, gathering usable data and transmitting it successfully back to Earth more than 4.5 decades later, from a location so far outside the solar system that it takes light itself, the fastest thing in the entire universe, over 20 hours to travel that distance in a single direction. And yet, precisely because that spacecraft simply refused to stop working, because its plutonium power generators kept producing just enough electricity to keep at least some of its instruments alive, and because a dedicated handful of increasingly specialized engineers at NASA's Jet Propulsion Laboratory have spent decades keeping 50-year-old spacecraft software and 1970s-era hardware running through what amounts to an extraordinarily patient, ongoing act of engineering triage, humanity ended up accidentally acquiring direct, continuous, in situ sensory access to an entirely new region of physical reality that had never once been directly sampled before in the entire history of our species. Every single measurement Voyager 1's instruments managed to collect and successfully transmit home now represents something genuinely and literally unprecedented. Actual physical data gathered from a place no human-built instrument had ever previously been able to reach or directly measure. Voyager 1's power situation continues to grow more precarious with each passing year, and that reality places a hard, physical, ultimately unavoidable ceiling on precisely how much longer this particular chapter of unexpected interstellar discovery can actually continue. The radioisotope generators that keep the spacecraft's remaining instruments and transmitter alive lose a small amount of usable power annually as the plutonium-238 fuel continues its slow, steady, entirely natural radioactive decay, a decay process governed by a half-life of roughly 87.5 years that nothing engineers do can meaningfully slow down or reverse. NASA's dedicated Voyager team has been forced to make increasingly difficult decisions in recent years, systematically and permanently powering down individual scientific instruments one after another, specifically to conserve just enough remaining electricity to keep the spacecraft's most essential systems, and crucially, its ability to communicate with Earth at all, functioning for as long as humanly possible. The stated internal goal at NASA is to keep both Voyager 1 and its twin, Voyager 2, operational and successfully returning at least some scientific data all the way through their 50th anniversary in 2027. A genuinely audacious target for two machines that were only ever originally designed and engineered to reliably function for about 4 years total. Eventually, inevitably, the ongoing decline of the RTGs will drop Voyager 1's available power below the minimum threshold required to operate even its transmitter. And at that point, the spacecraft will fall permanently, irreversibly silent, continuing to drift outward through the galaxy indefinitely, carrying its iconic golden record, a genuine one-of-a-kind time capsule containing images, sounds, and greetings in 55 different human languages, into a future so distant that our entire sun itself will likely have burned out and died long before Voyager 1 ever comes anywhere near another star system. So what does this whole strange, decades-spanning story actually mean in the end? It means that the boundary of our solar system, the specific place where the sun's influence finally gives way entirely to the vast, largely unmapped territory of interstellar space, turned out to be measurably busier, messier, and more dynamically active than any theoretical model built before Voyager 1 actually got there had predicted it would be. It means that even the most carefully constructed scientific predictions about the fundamental physical structure of the universe sometimes still require an actual physical instrument, genuinely present in that specific location, taking real, direct measurements before we can honestly claim to understand a place with any real confidence. And it means that a spacecraft engineered nearly 5 decades ago, running on power sources that are slowly and irreversibly dying, using onboard computer technology that predates the handheld pocket calculator, is still actively rewriting scientific textbooks today, simply by doing the one thing it was fundamentally built to do from the very beginning: keep listening patiently, keep transmitting faithfully, and keep measuring the universe honestly, exactly as it actually is out there, rather than settling for how confident, well-credentialed scientists sitting safely back on Earth had simply assumed from a comfortable distance of 22 billion kilometers that it probably ought to be.